Okay, so as Wally said, this will be the final lecture. Uh, Philip will start a new lecture series. You said starting next week, right?
That's
We're
right.
doing quantum field theory on the light front. So with this last lecture, I'm going to finish up talking about quantum mechanics on the light front using a single worked example. Uh, In order to address this example, I first want to review a few things from the previous lecture. So I'm going to quickly flash through some slides. So in my previous lecture 2 weeks ago, I talked first about doing quantum mechanics for one particle on the light front. I pointed out that for the transverse directions, it looks pretty normal. It looks a lot like non-relativistic quantum mechanics, and this is basically a consequence of the Galilei subgroup. You have transverse position and momentum operators that, in the coordinate representation, give you basically a C number valued transverse components and minus I times a transverse gradient. And in the momentum representation, your position operator becomes a gradient with respect to momentum. Your momentum operator, of course, just becomes momentum. Things get a little bit wonky when you look at the longitudinal component. Uh, and this is basically a consequence of the fact that there's a 1 over p plus in your Lorentz invariant momentum integrals. So in your coordinate representation, things look pretty normal. Your p plus becomes a derivative with respect to x minus, but with a plus I rather than a minus I, basically just because of the sign with which x minus appears in complex exponentials. But in the momentum representation, your x minus operator gets this very weird form. In addition to having your derivative with respect to p plus, there's also a minus 1 over 2p plus. This is actually fairly analogous to the Newton-Wigner position operators when doing relativistic quantum mechanics in instant form. So basically, all of your relativistic weirdness gets shuffled into your x minus uh, coordinate in a sense. As for two-body quantum mechanics, uh, I wanted to basically reiterate this Miller-Brodsky variable, which is kind of the equivalent of a two-body longitudinal separation. So the transverse separation is actually a really nice observable. It's invariant under all of your light front boosts, so it's a good thing to use as an argument in your light front potentials. But longitudinal separation is not by itself boost invariant. However, classically, P plus times a longitudinal separation is a good number. It is boost invariant. Uh, and actually, P plus in this separation commute, so this is a good quantum mechanical operator too. So we denote it Z tilde. It's often called the Miller-Brodsky variable. And in terms of a momentum fraction xi can be written in this fairly complicated looking form. Uh, and typically we parameterize two-body wave functions either in terms of a transverse coordinate separation and a light front momentum fraction, the momentum fraction being the portion of the plus momentum carried by a particular constituent, or we just use all momentum variables. Uh, Basically, no one, as far as I know, uses in actually solving for problems longitudinal coordinates themselves. Everyone uses this momentum fraction instead. So with those things reviewed, I want to look at the light front harmonic oscillator as a worked example. Uh, so getting the potential in the first place is going to be a little bit hand wavy. And I'm going to use the hand waving arguments more or less to get something that has the correct non-relativistic limit and is easy and reasonable to work with. So this slide's a little bit busy, but it's more or less a hand-waving argument for getting a nice light front potential. So this is a classical case. I'm not going to worry about operators failing to commute until the next slide. So non-relativistically, you have two bodies that form a harmonic oscillator. They're attached by a spring or something. The non-relativistic potential will be 1/2 mu omega squared and then separation squared. Mu here is the reduced mass. If we want to write it in terms of light front variables, first we need to separate r squared into a transverse separation and a longitudinal separation. And then we want to rewrite the longitudinal separation in terms of the Miller-Brodsky variable. Now, the non-relativistic formula is only going to be valid if both of the bodies are moving fairly slow. So we're going to say that this formula should be correct when both of the bodies are at rest. When both of the bodies are at rest, your total P plus up to a factor square root of 2 is going to just be the sums of the masses. So when the two bodies are at rest, in terms of the transverse separation and the Miller-Brodsky variable, you can write the non-relativistic harmonic oscillator potential like this. Now, how would we relate this non-relativistic formula to a light front formula? Well, we define the light front potential as basically being something that we would add to P minus instead of 2 P0, because P minus is the Hamiltonian, is the time translation generator. So we say 2 times P plus times this light front potential. Actually, that should probably be P minus potential, but because we typically absorb the P plus into light front, but that's fine. So this is well, if we subtract off P perp squared, it's going to be your Lorentz invariant quantity, your mass squared of your system, but we're assuming that everything's at rest, so big P perp squared is 0. So this should be equal to the instant form expression of the free energy, assuming that there's no interactions, plus the non-relativistic potential squared minus E free squared, because we're not including the free P minus here. So this is approximately equal to twice the sum of the masses times the non-relativistic potential, since the free energy when everything's at rest is just the sum of the masses. So we get basically product of the masses, because you can multiply out this m1 plus m2 times the reduced mass to get product of the masses, times omega squared, plus this basically r squared quantity in terms of the light front variables. Now, this should only work at rest. When your systems are not at rest, things are going to change because of the motion. First of all, in the light front, it's the P plus rather than the mass that serves the role of inertia. So this is going to be one of the hand-wavy steps. We're going to substitute the masses with the plus components of momenta to incorporate effects from relativistic motion. So m1 times m2 should basically be 2 times p1 plus times p2 plus, and xi times big P plus is P1 plus, 1 minus xi times big P plus is P2 plus. So we do this substitution. Secondly, frequency is not boost invariant. When you boost your system so that's moving away from you, you get a relativistic redshift. When you boost it so it's moving towards you, you get a relativistic blue shift. So we include a factor that goes as 1 over P plus squared in order to incorporate these red shifts and blue shifts. That's the second hand-wavy step. And when we include these factors, we get a light front potential that looks like this. We have our transverse separation, our Miller-Brodsky variable divided by sums of the masses squared, and this factor of momentum fraction times 1 minus momentum fraction. And an overall factor that we can call kappa to the fourth, because kappa has mass dimensions. Very similar looking forms to this are used by a whole bunch of people, not necessarily exactly in this form, but very similar to it at least, uh, as a confining part of light front potentials. Uh, so this is pretty neat. Now, before proceeding, we have a slight problem with this. Quantum mechanically, xi is a momentum fraction. It's a ratio of operators, and z tilde is also an operator. And these operators don't necessarily commute. P plus does not commute with z tilde after all. So first quantization is ambiguous. Which do we use? We can do a two-sided average. We can do something more complicated. I'm going to make an arbitrary and ad hoc choice. Uh, I'm not going to even make a hand-waving argument for it. It's just this is a quantity. You take square root of xi times 1 minus xi on each side of z tilde squared. This will be Hermitian because all three of these operators are Hermitian. And the reason for choosing it this way is that it just makes the math easier. The Miller-Brodsky variable in terms of the momentum fraction is this fairly complicated looking form with a 1 over square root of xi times 1 minus xi inside the derivative. So if we have this act on something that has a factor of square root of xi times 1 minus xi, these things cancel out. So we have a much simpler derivative. And the square root of xi times 1 minus xi here on the outside gets multiplied by the thing inside of the Miller-Brodsky variable, and you just get a xi times 1 minus xi times second derivative of your wave function by having this quantity act on your wave function. So it just makes the math easier. You'll get very similar results if you use these other operators. Not exactly the same, but you'll actually get the same energy spectrum for some reason that I don't fully understand. So our quantum mechanical operator for the light front potential looks like this. And the action of this potential on a mixed representation wave function in light of oh, I have a second derivative with respect to xi twice here. One of those should be removed. I'll fix the error in the slides before I share them. But we end up having that the action is pretty simple. You have an r squared times the wave function and a second derivative of the wave function with respect to xi times some stuff that's xi dependent. That's not too bad. If we recall that our light front Schrodinger equation is in this form, transverse Laplacian divided by xi times 1 minus xi here for kind of a kinetic energy term, transverse kinetic energy. We have some mass terms, light front potential, and this is all equal to what we typically call the Hamiltonian, because that's what we solve for as an eigenvalue problem. Then explicitly for the harmonic oscillator, we get this differential equation. It's a little bit long looking, but there is one nice simplification we can make right away, which is that some of these xi's times 1 minus xi can be absorbed through what's called the holographic variable. You'll notice that the first one in green in this equation always appears with an r perp, and this other one that's green here appears with an r perp squared as well. So we can define zeta as the square root of xi times 1 minus xi times r perp, and this will simplify the equation a little bit. This variable actually naturally appears in holographic QCD. You can read a lot of the works of Brodsky and de Terramon to see how it arises within the context of holography. Here, it's just a convenient change. Yes, Philip, you have a question or a comment.
Good morning. Holography, I think, was first discussed in instant time. So why would all this carry over to a light front without, or are you just calling this a holographic variable?
I'm just calling it a holographic variable. I just want to make mention to the fact that this variable appears when people are doing holographic light front QCD. Brodsky and de Terramon are really big advocates of it. I don't understand it myself, so I can't comment on it. I just know that this variable appears in their work a lot. But within the context of just working in four-dimensional space-time, it just seems to be a convenient change of variables.
Okay, thank you.
Sorry that I can't say more. It's holographic QCD is not something I really know anything about. Right. So with that we get a somewhat simplified equation because of this nice change of variables. Still a little bit ugly looking, but one of the nice things about it is that it's actually solvable. You can solve it by a standard separation of variables. Write the wave function as a product of three functions, each of one of the three variables it depends on. And this leads to three ordinary differential equations. One for phi, one for zeta, and one for xi. And each one of these looks a little bit more complicated than the last. And we end up having three coupled eigenvalue problems for the Hamiltonian, for something I'm calling lambda, just kind of an auxiliary variable, and ML, which actually has a literal interpretation as the quantum number for the z projection of orbital angular momentum. The first eigenvalue problem is trivial. This is like simple stuff. It's just a complex exponential or a sinusoid. Continuity requires it to be an integer, and it's just the z-axis projection of the orbital angular momentum. That's simple enough. The second eigenvalue problem is for this zeta, which describes the transverse coordinate dependence of your wave function. So this is actually just the 2D harmonic oscillator. It's basically, if you open up Shankar's quantum mechanics, it's exercise 12.3.7. So you can follow that pretty simply. First, you define unitless variables to somewhat simplify the equation. And then you factor out an e to the minus 1/2 tau squared in terms of this unitless variable tau, kappa times zeta, because you know that the long distance behavior of a harmonic oscillator should look like that. You get a new differential equation doing the substitutions. And you also know that the short distance behavior of a harmonic oscillator should go as distance to the power of L, or in the 2D case, ML, since that's effectively your angular momentum quantum number. So you define another auxiliary function, y is tau to the ML times F. You find the derivative, second derivative, substitute them in, and you get this nice looking equation. I'm not aware personally of explicitly tabulated solutions to this, but you can use the standard series expansion method. You can say that f has to be some sort of infinite series in tau, and you can derive a recursive relation for the coefficients of this. You find that all the odd coefficients have to be zero, and the n+2 coefficient depends on the Cn. And in order for this to not blow up and for the series to terminate, you need that this capital lambda is equal to some, well, for some integer big N perp is equal to this combination of N perp and your other quantum number ML. You also know that N perp has to be even, since all of the odd coefficients are zero, and you can solve for the lowercase lambda, the unit full one, as being 2 times kappa squared times this combination of quantum numbers here. The third eigenvalue problem is probably the more complicated of the three, but it's also solvable in a pretty straightforward way. So we have the second order differential equation for x of xi. You again define some new dimensionless constants in order to make the equation less of a handful, you end up with this second order differential equation. Now, for physical reasons, you expect the wave function to vanish when xi goes to 1 or to 0. The reason being that when xi is 1, one of your particles is carrying all of the p plus, and the p plus of the other becomes 0. The probability of that should go to 0. And likewise, when xi goes to 0, you end up in the reversed case. The other particles carrying all the momentum, and the probability for that should go to 0. So we expect some endpoint behavior. We expect the wave function to go as xi to the a when xi is close to 0, and 1 minus xi to the b when xi is close to 1 for some a and b that are both positive. So we can deal with this in 2 steps. We can do a substitution where we say x is equal to xi to the a times y xi, and then y xi is equal to 1 minus xi to the b times f of xi. We can figure out what a and b are by canceling the 1 over xi and the 1 over 1 minus xi in this differential equation. So we have the differential equation as the starting point, and we do the first substitution. The second derivative of this substituted function in terms of the new function can be written in this form. We pull out a xi to the a, which we're going to divide the entire equation by to make it simpler. And by putting the substitutions in, we end up with a new second order differential equation for the new function. And you can gather terms that go as 1 over xi. One of them from the second derivative of x comes from this term, which is multiplied by the xi here. You get an a times a minus 1, and in order to cancel the 1 over xi term, we need a times a minus 1 to equal mu1. So that's how you determine what a is. There are technically 2 solutions to this, 2 solutions to the quadratic equation, but only one of these solutions has a greater than 0 in the limit of large mass, and we need a to be greater than 0 for the wave function to vanish instead of explode. So that determines what a is. So this gives us a differential equation for y, and now we need to do the other substitution to determine what b is. So we substitute in y is 1 minus xi to the b times f of xi. We find the derivative and second derivative because both of these need to be substituted in. And if you do all the algebra of multiplying everything out, I'm not going to walk you all through step by step for this. You end up finding that the stuff that is divided by 1 minus xi, you have a xi times b minus 1 minus mu2. And in order to not get this to 0, but get this to no longer be something going as 1 over 1 minus xi, you need b times b minus 1 to equal mu2. So then you get a xi minus 1 divided by 1 minus xi will just be minus 1. So similar to how there are 2 solutions, but only one of them will be physically valid at large masses, we find b is this quantity related to mu2. So we can rewrite the differential equation. It has a simpler form if we write it in terms of a and b than if we write it in terms of mu1 and mu2. So I wrote it in terms of a and b, but a and b are related to mu1 and mu2 through these formulas. So this is the resulting differential equation. It is simpler than the previous than what we started with because there's no longer anything with 1 over xi or 1 over 1 minus xi. So this one's actually solvable using the standard series expansion method. You can, if you write it out as an infinite series with coefficients Cn, you find that for this equation to be valid, you have to have this recursion relation for the c's. This should actually be multiplied by Cn here, another typo. So Cn plus 1 is this quantity times Cn. So kind of like in the two-dimensional harmonic oscillator, the other eigenvalue problem, in order for the series to terminate, there needs to be some particular n, going to call it n parallel since this equation describes the longitudinal dependence of the wave function. There's some n parallel for which this entire quantity in the numerator vanishes. Oh, another typo. This mu here should be mu0. I'll fix these typos before sending it over the slides. Apologies for that. Yes, Philip.
I looked at this very quickly, but your equation at the top looks like it's the hypergeometric equation, which has an exact solution. I made a mistake. I think it is.
I'm actually not familiar with it, so I wouldn't know. I did talk with Jerry about this, and he did find exact solutions for it.
Yes. It is the solution is a hypergeometric function.
Ah, that's very neat. Thanks for pointing that out.
Yeah. Okay.
So the series terminates. I guess it's the result is equal to the hypergeometric function, although I'm not really all that familiar with it. I'm only familiar with it in name. I've never worked with it. But based off of this argument and putting together the solutions to the other eigenvalue problems from before, you find that the spectrum of this m² operator is equal to this fairly complicated looking expression in terms of the three quantum numbers ml, nperp, and n parallel. Recalling that A and B are related to the masses of your system, of your constituents by this formula, where the 1 here is for A, the 2 here is for B. So this is pretty complicated looking, and perhaps the first thing you might think is this really the spectrum of the harmonic oscillator? Is this really reasonable? We know what the spectrum of the non-relativistic harmonic oscillator looks like. In 3 dimensions, it's just omega times 3/2 plus n for some principal quantum number n. Well, the next task is to show that this spectrum does at least make sense when we take the non-relativistic limit. So the non-relativistic limit in this case means that your masses are significantly larger than this spring constant kappa. So if we take A and B in this limit, then this 1 under the square root is negligible. So we can write A and B as 1/2 plus, well, the square root of this other quantity. We multiply out the 1/2, so we get a 1/2 plus either of the masses times the sum of the masses divided by kappa squared. And it turns out that only the sum of A and B appears in this equation. So when you take the sum, it's 1 plus square of the sum of the masses divided by kappa squared. So this means that in non-relativistic limit, big M squared is equal to sum of the masses squared plus kappa squared times 3 plus 2 times this combination of the 3 quantum numbers, plus a higher order thing, a kappa to the 4th thing, which we'll consider relativistic corrections. Now, if we recall that the masses are considered part of the energy relativistically, so for when the system's at rest, the mass squared of the system is the sum of the masses plus what you call the non-relativistic energy. Square that, multiply it out, and drop the order ENR squared terms, and compare this to the result that we got in purple, we find that the non-relativistic energy, substituting in kappa squared is the sum of the masses times omega, is exactly omega times 3/2 plus some combination of quantum numbers, which is exactly the usual non-relativistic spectrum if this combination of the light front quantum numbers is identified with the principal quantum number of the non-relativistic oscillator. So at the very least, this makes sense as a relativistic generalization. Yes, Philip.
I'm sorry, I just missed a very simple point. These n perp, n parallel, and ml are all positive integers?
Yes, or zero or plus
Zero, but no negative energies.
non-negative.
Thank you.
Important that the zero possibility is there because we know the ground state energy has the n equals zero. So that's a good point to bring up. Thanks. So there were some hand-waving arguments that went into getting the potential, largely motivated by having a simple problem to demonstrate that you can do quantum mechanics with potentials on the light front. But at the very least, it's a sensible relativistic generalization that has the correct non-relativistic limit. So as for the wave function, well, every one of the states is going to have a different wave function. Let's look at the ground state. That's when all of your quantum numbers are zero. You have trivial phi dependence, of course. Your z of zeta dependence is just going to be given by this Gaussian function. And your x of xi is given by basically the product of your endpoint behaviors. Recalling as well that zeta is equal to square root of xi times 1 minus xi times r perp, and that your wave function is the product of all these three things. The ground state wave function is up to a normalization factor, which I didn't calculate, xi to the a times 1 minus xi to the b, times this Gaussian function with xi times 1 minus xi times r perp squared, and of course your kappa squared. You can get excited states by using the recursive formulas for the polynomial coefficients. And as Philip pointed out, conveniently, the x of xi actually does have a tabulated solution in terms of hypergeometric functions. Now, one last thing I want to look at. This is going to be a fairly short lecture, I guess, to make up for all the other times I went overtime. It's also interesting to look at the density in xi. So the density is defined by integrating out, the xi density is defined by integrating out your other variable dependence, in this case, your r perp. And we also want this density to be normalized so that when you just integrate out xi, you get 1, which means we need to put the element, the factor 1 over 4 pi times I times 1 minus xi from the integration measure into the definition. So move that over here. Applying this to the harmonic oscillator ground state and ignoring normalization for now, we can restore the normalization later. You end up getting from this 1 over xi times 1 minus xi, an extra factor of minus 1 of each of these. Since you're squaring the wave function, you get 2a and 2b here. And there should be a minus and a kappa in this equation, the exponent. Seems like I have a lot of typos to fix before sending over those slides. But once you actually fix the negative here, so the integral actually converges, you'll get an extra factor of 1 over xi times 1 minus xi. So you'll have xi 2a minus 2, 1 minus xi, 2b minus 2. So what does this mean? For some intuition, it might be helpful to look at the equal mass case and to look at either the two bodies having very small or very large masses. So in the equal mass case, A and B are the same. And you have this nice looking formula with the square root here. If the mass is extremely small, then you can do a series expansion for this. This should be 1/2 here instead of 1. Sorry for the very large amount of typos in this lecture. But basically, you can do the infinite binomial series for this and terminate it. You end up getting a 1/2 times the 1/2, giving you a 1/4, hence the factor 4 here, but this should be 1/2 times it. And then for the large mass limit, you just neglect the one here, and you can even neglect this other one. So you end up with 1/2 times the square root of this quantity, which is how you get this. Uh, Once you actually account for the correct factors, the distribution becomes flat. Oh, sorry, I was being stupid there. There isn't a typo here. It's because the ones combine and it cancels out the two. Anyway, the distribution becomes flat. The power goes to 0 in the massless limit, and the supermassive limit gives very high powers. So here I have a plot kind of demonstrating both of these limits as well as a mass imbalanced case to give a bit more intuition. Uh, the momentum density, light front momentum density with the normalization factor restored, it's just a beta function. Looks like this into both of your limits. Once the masses are really small, you get something that looks almost flat, but then falls steeply to the edges at xi near 0 and xi equals 1. So basically, the interpretation of this is that uh, if the partners are both nearly massless, then it's really easy to have them moving arbitrarily quickly and to be carrying nearly all of the forward momentum. On the other hand, if they're both extremely massive, then it's a lot harder for one of them to carry all of the P plus. Since mass already contributes to the P plus, you would need to be moving with an extremely high forward momentum in order to kind of overpower the mass of the other constituent contributing to the P plus. And also, if the two bodies are very massive, it's less likely that they'll be moving at extremely high longitudinal velocities. So you end up with something that's sharply peaked around xi of 1/2 for large masses, nearly flat for very small masses. And if you have a mass imbalance, the heavier partner is more likely to have more P plus just because it has more mass, and mass contributes to P plus when the system is at rest. So that was basically the worked example that I had, which means that the lecture is more or less finished fairly early, 20 minutes early, unless people have more comments or questions.
Thank you very much, Adam.
Yes, Philip.
Yes, let's have some questions. Philip,
Well, does anybody else want to go first?
you're the only hand raised
Okay.
so far.
Just as a matter of curiosity, I've got quite a few questions, but the first one is, does this give anything like the charmonium spectrum?
I wouldn't necessarily expect it to because charmonium is described by the Cornell potential instead of a harmonic oscillator.
Yeah, I know, but you're advocating that this is a mechanism for confinement. So
Uh,
maybe
I'm not so much advocating it, but saying that a lot of people have used as the confining part of their potential.
no, I understand that. When I say you, I don't mean you
Okay,
personally.
fair enough, fair enough.
When people do confinement, I'm not quite understood why they want to use harmonic oscillators since we know that charmonium works with a linear potential. That's why I raised the question.
Yeah, that's a good question. I haven't done a comparison. I wouldn't expect it to describe it, but again, I haven't done it, so I don't know for sure. I also can't really speak to why people use the particular potential they use. In my opinion, the main thing with the harmonic oscillator is that it's mathematically simple.
Yeah.
Because it's an R squared, you end up getting this R perp squared plus the Miller-Brodsky variable squared. Whereas with a linear potential, you would have that under a square root. And well, the
No,
Cornell potential, as far as I know, is not solvable analytically. It has to be done numerically anyway.
let me just be very clear. As far as what you've done what you presented this morning is a very nice way of analyzing the harmonic oscillator, and we shouldn't pretend otherwise. I just was curious as to where it would lead. That was that.
Yeah, yeah.
But I know you're just giving it as a worked example.
Yeah, yeah. To be honest, I don't really know of I don't know how realistic it is as a confining potential. I know some folks use it. I don't know offhand whether it gives the right spectrum. Maybe some of those folks in the audience are willing to answer and might know something. My intuition is that the Cornell potential should be used instead, but there might just be something that I don't know or I don't understand that makes the harmonic oscillator work out when you're doing light front instead of instant form. I honestly don't know.
Could I jump in here and just make a few comments?
Sure.
And thanks. Thank you very much, Adam, for this wonderful presentation. Couple initial comments is that the 3D harmonic oscillator with one frequency is, of course, an interesting limiting case. One can also think about, since you're doing light front variables, having asymmetry in the frequencies between the transverse and longitudinal directions. I don't know. Did you look at that?
No, I haven't, but that's actually a interesting suggestion. I haven't
Yeah.
looked at it though.
Yeah. And the reason, okay, now let me make another comment. So in basis light front quantization, we use this 3D harmonic oscillator potential so far with just one frequency,
Mhm.
in a couple of ways. One, in the initial applications up until recent times, we actually kept the phenomenological confining potential in the Hamiltonian. But in most recent applications, we actually drop the harmonic confining potential in
Hmm.
all directions and just use pure QCD interaction vertices and start expanding the Fox sectors to see what we can get. So, but the 3D harmonic oscillator in light front coordinates serves as our basis functions for
Hmm.
solving the quantum many parton problem that we then encounter. And it turns out that we can separate the transverse uh, functions from the longitudinal functions, and then sometimes we don't use the um, functions in the longitudinal direction coming from the oscillator, but actually go back to discretized light film quantization. It's
Hmm.
really a question of convergence properties and whether practical numerical applications converge faster with one basis than another. It's also a matter of some numerical convenience, um,
Hmm.
especially in the longitudinal direction, which way you go. But a lot more is being written and being investigated in these directions, and some of this will be forthcoming in the near term.
Awesome. I'm looking forward to it, and thank you for your comments.
Wayne, you had a question?
It's more a comment on Philip's question. There's another way to do the oscillator, and that's if you just take, let's consider the simple case of equal mass particles. The invariant mass is just the square root of m squared plus some k squared, and that k squared kinematically is actually an kinematically invariant variable. And if you just replace that k squared by k squared plus a Laplacian in k squared, you get another version of a relativistic harmonic oscillator. And the interesting thing is because that oscillator is in the square root, you actually do get linear confinement and you get Regge trajectories. So
Oh,
it's a question of how the mass is related to this oscillator thing. And I think the same thing happens in the way you did it, Adam. Probably have to work through, and yours is more complicated to understand exactly how things behave. But
yeah.
I think that's the same thing, is that the fact that you have a square root of the oscillator that is involved in the spectrum, and that, at least asymptotically for large masses, gives you linear confinement.
Hmm. Interesting. Any chance you could send me any references you know of on that later? I'd like to read up
Yeah,
on it a
I'll
bit.
be happy to send you some stuff. Sure.
Thank you.
Yeah. If I may just comment on Wayne's comment on my comment. Um, what I think might be able to address the issue that Wayne has raised is to take, Adam, to take the solution that you have and convert it back into instant form
Hmm.
and see what kind of a spectrum the instant form people would finish, what kind of a theory that the instant form people would finish up with.
Yeah, that would be interesting to look at.
I'll make another comment on that if that's okay. Um,
Of course.
there's one way to, there's, if you look at sort of the equivalence between light front, instant, point form, one way to handle that is to basically you start with the mass operator and then you put the overall kinematic variables around them. And if you do that, all three forms have the exact same spectrum. And it constrains how you do the spin and things like that, but that's one way to understand the equivalence. And the mass operator is an invariant thing kinematically, and what you're effectively doing, you put an interaction in terms of relative variables, and then you put delta functions in for p plus and p perp or
Hmm.
p vector, and at the end of the day, the mass spectrum is still the same.
Yeah. It would also be interesting to do the comparison because right now I have no intuition as to what the n-perp or n-parallel here mean. It would be interesting to see what combination of them actually maps onto, say, L uh, in the instant form case.
Hey, are there any further questions or comments? If not, let me thank you, Adam, once again for what has been a tremendously useful and enjoyable series of lectures. We're all very grateful for the effort that you've made in putting them together. So I'd like to ask everybody to give you a round of applause.
Thank you, Wally.
How do we do that?
Hey, so as I mentioned earlier, um, next week we will have the first of several lectures by Philip Mannheim, and I will send um, details about the content of those lectures shortly. As usual, a recording of these lectures and the slides will be at the usual places, which I will send in the next announcement. Okay, so thank you very much, and look forward to seeing everybody next time. Bye-bye.